Now, it's my absolute pleasure to be able to introduce Professor Sir Peter Knight, FRS, to you. So Professor Knight is a chair of the UK National Quantum Technology Programme Strategy Advisory Board and has been involved in the creation of the UK Quantum Programme since its inception, including the creation of the UK Quantum Strategy. He chairs the Quantum Metrology Institute at the National Physical Laboratory and is Senior Research Investigator at Imperial College, where until 2010 he was Deputy Rector, responsible for the college's research strategy. He was knighted in 2005 for his work in optical physics, and until 2010 was chair of the UK Defence Scientific Advisory Council and remains a UK government science advisor. His research centres on quantum optics, non-classical light and quantum technology, and its application in sensing, timing, communications, imaging and computation, just a few things. And I can't read all of Peter's accolades, we'd be here all night, but he has won the Thomas Young Medal, the Glazebrook Medal of the Institute of Physics, the Ives Medal, I'm going to stop, he's telling me to wrap it up. Many medals. Thank you very much for joining us. We can't wait to hear your talk.
Right, so we're going to a change of tack now because what we've heard is the work of a really gifted experimentalist working with a wonderful team in Stanford where they created that stuff. I'm going to talk about what other people have created, okay? A little bit about what we did, but not very much. Right, so this year is the International Year of Quantum, okay? For reasons that escape me, I'm chairing it for the United Nations. So let's have a look at what we intended to do, what we are doing. In June in 24, the UN General Assembly declared 2025 the International Year of Quantum. It was led by Mexico and Ghana. So Mexico got it through UNESCO, Ghana got it through the United Nations. That's why we're going to have the closing event in Accra, in Ghana, in February. So our mission, it's 100 years since quantum mechanics started. Our intent is to raise the public awareness of what quantum has done for the way that we live our lives throughout the world. Okay? To raise public awareness, looking at the impact, but especially to inspire the next generation of young people in the area. We've run a number of global events, quantum innovation, quantum ethics, hackathons, and so on, really to inspire a whole raft of people. Events here in Australia, for example, the fabulous road trip that goes right across Australia, meeting people in townships that may not have ever met a scientist before. Okay? Right. So as I say, this is the International Year of Quantum. We raised $1 million for the global part of the program. Now, what is quantum? Now, some of you in the audience are absolute experts at this, so you can go to sleep now, okay? And those that aren't, we can go through some of the bits and pieces of what quantum did. And it's come in two phases, the first quantum revolution and then the second one. Going back to 1925, the idea that things were quantized, in other words, that they had energies that came in discrete, not continuous distributions. Okay? So energies are discrete, and there are energy levels. And therefore, you could have transitions between those energy levels that would generate light, for example, at specific frequencies. They also discovered that matter had a particle behavior, but you could also diffract it, and it had a wave-like nature as well, so duality. The idea of superposition is the most counterintuitive part that you don't really experience in the everyday world, except that every single one of you who drove here today used it. Okay? Imagine a system where I can be in this state or that state. That's what you see classically. We can put it in this state and that state at the same time, That's a superposition. You used it if you drove here, because that's how GPS works. GPS for sat-nav is talking to atomic clocks, and those atomic clocks are in superposition, so you've used it. Okay. And then entanglement, which is one of the really freakier parts of this, the idea that you have a bipartite system, one over here, one over there, an observation here, allow you to infer information about over there. It does not imply superluminal communication, by the way. All right, but never mind. It has some extraordinary things that enables you to do. Right, so the first quantum revolution changed your world. I mean, it led to broadband, lasers, microelectronics, all are enabled by that first quantum revolution of the idea that you could run systems with discreteness, but you could tunnel through barriers. That's how semiconductors work. So much of our modern technology is dependent on that first quantum revolution. All right, so some takeaways, though, of what we need to understand about the material world when quantum is the dominant part of it. So I've got 4 key things, takeaways. In particular, the idea that we grew up with from Newton onwards, that materialism was something that really was characterizing the world. The end of local realism is really something that we have to infer from modern quantum mechanics. That everything in the world is connected through entanglement, making the world non-local. The end of strict determinism, and the fact that you would get randomness intrinsically in nature because of quantum. And also, it restored the human observer to that central role when you make a measurement. Okay, so they're the 4 takeaway things, and I'll try and illustrate them as we go along. So we're used to the idea of randomness. You get probability. After all, if I throw a ball into a field, I've got a probability where it is. Okay, easy, classical probability. But the fact is that it was somewhere. You just didn't know it. Okay? Quantum probability is actually very different. Okay? You mustn't say it's there, but I don't know where. Okay? There are examples which are contradicted by experiment. So quantum amplitude interference is more than just ignorance. It really rests on the ability to know. Right, so the founders. Okay, a long history. You see anything very strange about that? They're all blokes. Really rather sad, isn't it? Never mind. If you look at the Solvay conference, which is the really famous picture of the quantum discoverers, one woman, Marie Curie. She did, of course, win 2 Nobel Prizes, so that's something worth bearing in mind. So Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, Max Born, Paul Dirac, Erwin Schrödinger. These are the founders. There's a nice definition of, it's too busy to read, on what entanglement is due to. It's due to Erwin Schrödinger in an essay he wrote in the Cambridge Philosophical Society. Right, so they're the founders. How did it start in 1925? In 1924, the beginning of 25, physics was in a terrible mess. Ability to try to interpret what was going on, people were getting desperate. There was a Kramer's Bohr-Slater paper that even contemplated the abolition of causality and of conservation of probability. Pretty desperate measures. Okay. So, 1925, this person, Werner Heisenberg, suffered from extreme hay fever. Okay, and he was sent off by his boss, Max Born, to Helgoland, where there was no grass pollen. And during that time, he started to look at what was going on with this Kramer's formula, what's called the dispersion formula. And there were things that are really scattering things in the Kramer's dispersion formula. that he started to interpret already as amplitudes. Why he made that jump is uncertain. Okay? Amplitudes already imply interference. Okay, so during that hay fever period, that's Helgoland in that picture at the bottom there. He came up with the idea that there were these quantities that described these scatterings, but they were peculiar. If you wrote them that way round, it was different to that way round. Okay? Now, we all know what that is. Most of us know what that is. Okay, but he didn't. Okay, off he goes. He goes to talk to Pauli. That's Pauli. Pauli was the champion doubter. He's the person you bounced ideas off, and he would destroy you if it was ludicrous. Okay? Right. But Pauli said, wow, there's something here, and he encouraged him. All right? Went back to Born in Göttingen, and Born said, aha, things that are like that, but different like that, they're called matrices. Matrices weren't taught in physics courses, okay? But Born had been to Courant's and Hilbert's mathematics courses. Right, so he said, all right, they're matrices, and he started to worry about these matrices, and no, there are very few equations, maybe 2 in my talk, okay? This one is the commutation relation between position and momentum, okay? And it was Born that derived that. I'm very keen on making sure that people get the right credit if they can. Right, having got that, then he had basically an idea of how he could begin to develop a theory of atomic matter. Right. Pascal Jordan is involved in this as well. And so the famous 3-man paper, Heisenberg, Jordan, and Born, set out the basic theory of matrix mechanics. Right. Now, something weird was going on, because across Europe, people started to worry about something else. De Broglie, in his own thesis, was concerned to demonstrate that particles could also behave as waves. Okay? So, Schrödinger was a professor at the University of Zurich. They had a joint colloquium with ETH in Zurich, led by Peter Debye. That's Debye on the top. Okay? And they had a seminar on de Broglie's waves. Okay? And Peter Debye stopped the seminar dead and said, it is childish to talk about waves without a wave equation. And he turned around to Schrödinger, who was sitting right behind him, and said, Schrödinger, you're not doing very much at the moment. Why don't you look into a wave equation for these waves? Okay, I bet he wished he'd done it himself, by the way. Right. I know this to be true. Felix Bloch was in the audience. Felix Bloch was my first boss in Stanford about 1 million years ago. All right, so that's the beginning of the Schrödinger approach to this. There's another person now. Okay, that's Paul Dirac, a PhD student of Fowler's in Cambridge. Heisenberg visited Fowler in Cambridge, and there was a dining club run by Peter Kapitsa, and he presented his ideas. Dirac almost certainly was in the audience and thought, wait a minute, these matrices, these are kind of strange. We need to link it with a dynamical theory, okay? Remember, he's a first-year PhD student, okay? Right, bam, next year he's got his thesis, okay? It's called quantum mechanics. Okay, I went to the University Library in Cambridge to find the thesis. To my delight, it's handwritten. All the crap we put students through making tech versions of their thesis, Dirac has a handwritten thesis, and it's called quantum mechanics. And in that, he linked it to dynamics through the Poisson bracket. He introduced the ideas of C numbers and Q numbers. annihilation and creation operators, solution to the Zeeman effect in magnetic fields. All of that was in his thesis. Okay? Right. Okay. So now we're going to jump ahead now. So we know we've got a theory which talks about the de Broglie waves and a wave equation. We've got matrix mechanics. We've got the dynamics of a whole raft of things. Everything hunky-dory. But Einstein was extremely worried by the implications of this, and especially about whether quantum mechanics was a final theory that actually had an understanding of the final. So they produced a paper. You can't really read it, but that's in PhysRev. It's called the EPR paper. I love the fact that New York Times featured it on the front page. Einstein attacks quantum theory. Scientist and 2 colleagues. Implication is the other 2 weren't really scientists there. and sadly, it was actually written by Podolsky in the first place. Right. And what he was talking, and I've pinched this picture from Jim Al-Khalili, who talked about this last week at the Royal Institution. Right, so we've still got this business about is quantum complete? How do we understand entanglement? Right, so a defense of all of this, another contribution for Erwin Schrödinger, and he introduced the word, well, he didn't introduce the word entanglement first. He introduced the word verschränken, okay, which you loosely translate as entanglement. Verschränken, right, look, my arms, and that's verschränken, right, good. All right, so not only did he introduce entanglement, he introduced this poor cat, okay, which is in a superposition because the poor cat in a box, there's a radioactive source and a Geiger counter attached to a hammer and a flask of poison, and the radioactive source could go off or not, okay, so it could trigger the hammer and kill the cat or not, so until you open the box, you're in this superposition. So there's Schrödinger's cat, and 12 years after that EPR paper, he was still worrying about all of this lot, wrote to Max Born, and he used for the first phrase, a phrase that I absolutely detest, called spooky action at a distance, because it implies it's supernatural, and I think we ought to avoid that. Right, so we've got this peculiar view of the world. Schrödinger with his continuous waves and a wave equation, but we have outcomes and then you do measurement, okay? And the way you understand this is often that we talk about quantum jumps, okay? Schrödinger hated quantum jumps. He liked continuous evolution of things. He called them quantum jerks even, okay? And there's a nice quote, you can't probably possibly read it. If all this damn quantum jumping were really here to stay, I should be sorry I ever got involved with quantum theory. Right. And at one point, he actually said, we're not experimenting with single particles any more than we can raise ichthyosauri. It's the only way of biology I can get into the field, by the way. Right, ichthyosauri in the zoo. Okay, there's an ichthyosaur, basically a fossil, ancient animal. But of course, we do raise ichthyosaur in the zoo because we can play with single quantum systems now. Okay, for example, we can trap single ions, and those single ions can be illuminated by laser light, and we can watch them jump from state to state. Fluorescence turns on, turns off, like an atomic lighthouse. Here's a string of ions, and they're the jumps between fluorescing states and non-fluorescing states. Okay, so we do see quantum jumps, and we can see individual quantum systems. Right, so we can do that. Now let's come back to these correlations, and in particular John Bell. John Bell was one of my heroes, an Ulsterman from Belfast, and he was worrying very much about the foundations of quantum mechanics as his hobby. His day job was an accelerator engineer theorist at CERN. Okay? Right. a wonderful character worried about whether you could quantify these entanglement correlations in a measurable form that you could go in and do experiments on to demonstrate whether things were local or not. Okay, so there is John Bell, much earlier stage on the right-hand side, with his idea of a source that could come out with two particles, and you could measure the correlations between those two particles. Okay, there's Alan Aspey, my friend with the most wonderful moustache. And what I really thought was a marvelous thing is the city of Belfast named a street not after a person, but the theorem. Does anybody know a street named after a theorem, apart from that one? There is a street in Belfast called Bell's Theorem Crescent. Okay? I've been there. It really is true. So there's John Bell. And what he's saying is we can test these entanglement ideas of locality. And these are the people that did it. Okay, right in the middle, John Clauser, very early experiments in Berkeley. I know this is being videoed, and it will be on YouTube. John did not get tenure at Berkeley because he was told, you're just testing quantum mechanics. Everybody knows it's true. Okay? And he went to Livermore to design bombs. True. Then Alan Aspey, wonderful way of improving the stuff. And then Anton Zeilinger using a more photonic system. They shared the Nobel Prize in 22, really making sure that we understood with as few loopholes as possible the way that nature is actually correlated and shows this non-locality. Of course, there are other ways of looking at quantum phenomena, and I'm delighted to show this picture of this year's Nobel Prize winners in this, and in particular for those of us who transitioned from the Equus Center of Excellence of the ARC to the QUBIC. John Clark was on our advisory board for at least a decade on this one. Really wonderful that these people have been recognized for their work. Right, so the second quantum revolution. Now we've got the idea that we've got superpositions and we've got entanglement. Let's see how we can exploit them. Okay? Now, if we have the right tightly controlled environment, we can do that. And that's how an atomic clock works. Atomic clocks give you GPS. So we need to look at other ways in which we could do this. And the big problem is that our funny superpositions are fantastically fragile. A little bit of engagement with the rest of the world, and your superpositions go away. We have a phrase for this: entanglement is monogamous. Can entangle those two. Okay, if I entangle with something else, I've got issues. Entanglement is monogamous. Okay, right. Right, so that's called decoherence. Now, everybody in the world has now joined the adventure in terms of this. So what I'm going to do is go through the national government commitments, not the private ones, not the company ones. Okay? That's China with a minimum and a maximum. It's really hard to nail it down precisely. It's got big error bars. So that's John Y. Pan's program, that's the USA program, that's my program in the UK, and so on. I'm going to pick on one right down here, which is a really super important one, where the intervention of one particular foundation doubled their spend. Okay, that's Denmark, the intervention of Novo Nordisk, who understood that quantum could transform healthcare, doubled the spend in Denmark. Right, so everybody's at it. All right, so what could you do with this quantum superpositions? You can do quantum computing and simulation, obviously. And we built these National Quantum Computing Center test beds where we can kick the tires on platforms. You can do sensing, imaging, timing. Daniel Fascio is in it somewhere, looking after that. There he is at the back, as part of that enterprise, leading that work. Quantum networking, and right at the center, industry-led challenges. We've built all sorts of infrastructures. For quantum technology, I've got one takeaway message. I don't care if you forget everything else. Just what's going to come next is your takeaway. It ain't just quantum computing, all right? And the quantum computing is a longer journey. Quantum sensing and timing, will make sure it changes your world much more quickly. Right, so some real world applications. I'll start right down here. You can build gravity sensors. These are our cold atom ability to sense gravity. Okay, so gravity sensors commercialized out of the University of Birmingham with a spin-up called Delta G. You can start working out ways in which quantum computing machines could be interfaced with data centers. The data center of the future, that's that one. And that's an Orca machine sitting in a data center. We've done the first commercial trial of a quantum secured network around the City of London. That's run by BT with Toshiba, and it's for HSBC, the bank. Okay, right, then you can do all sorts of wonderful things with quantum correlated single photon cameras that could detect greenhouse gases. Okay, so that's what's going on there. Let's spin out from the University of Bristol using the single photon emitted detected cameras detecting methane, working, their spin out is called QLM, working with Schlumberger. Right, what's the child on the left-hand side being tortured with? Okay, that's brain imaging, and I'm going to come to that. It's a MEG system. Many of us call it a MEG system because we cannot pronounce what MEG stands for. I'm going to try. Magnetoencephalography. Did I get that right, roughly? Nearly. Okay. And so what that is a whole load of optically pumped magnetometer cells in a helmet, and already that's being used as a research tool to understand juvenile epilepsy. I'll come back to that in a moment, but you know, if you didn't use an OPM helmet structure, you would put that child through really quite a distressing environment, putting them through a big superconducting tunnel MRI machine. It's really scary. That child can run around while we look at it. So let's have a look at some of these applications. I really hesitate to say this in front of Daniele at the back, but never mind. You have to shut your eyes at this point. Ghost imaging. This is one of the more peculiar things in quantum mechanics. And I'm not winding you up with a specious science fiction episode. What you can do is we can now make correlated beams of light, red light and blue light, that are correlated. And the way we do it is through nonlinear optics. An ultraviolet beam comes in, a nonlinear crystal, could be BBO for example, out comes a blue and a red photon, and red is great for biomedical applications. It gets through tissue and blood. The cameras are appalling and expensive, okay? Blue, you've got at least 3 really good cameras in your phone, okay? So what you do is, this is the thing that's being imaged, and that's your camera looking at the blue light. That blue light never touched the object, okay? But because we can use the fact that these things are born together, they're correlated, you have a bucket detector that says to the camera, a photon's coming. Okay, and that gives you the image on this sort of stuff. Okay, so that's ghost imaging. Great deal of work done in Rochester by Bob Boyd and by Miles Paget in Glasgow. And it works beautifully. You can see lots of other applications. If, on the other hand, you could say, oh, I could actually use the entanglement properties. Sometimes it's called imaging without detection. Now you can start to do all sorts of other fancier things. And the collaboration that was funded between Imperial College and Glasgow through our Quantic Hub, and the young woman very much as part of the engine for this was Emma Pierce. And what she did is she built an entanglement camera. And the entanglement camera improved the resolution of imagery that's used by oncologists. Okay? Imagery for oncologists is bad news. And they have to determine whether or not the patient goes for chemotherapy and radiotherapy. 27% of cancer deaths in 2009 were due to unnecessary chemotherapy because they were playing safe. Okay? So if you can improve that resolution, you can save lives. Okay? Chris Phillips, who was involved in the imperial end of that, has commercialized it through his startup company called DigiStain, and it's being used by oncologists. Right. So coming back to the biomedical side, which is what this week's work is all about, with QBio, with QUBIC, with QLife. We're going to run out of words that have to start with a Q, by the way. Right. Right, it's less invasive, it could be cheaper, it could be portable, it could be small, it could be more precise, it could be more sensitive. If it ain't any of those things, you don't need it. I'm coming back to something that Michael said this afternoon in terms of translation agenda. You better make sure you've got something that is of value, okay? And what quantum sensors can do is match all of those things if you're smart. So better access, non-invasive monitoring, earlier and more accurate diagnosis, like the DigiStain oncology, and so on. So we got this hub. It's called QBiomed. It looks suspiciously like a copy of Warwick's. I think they're independent, but they've got lots and lots of resonances between them. Okay, and it's run out of Cambridge, UCL, and Warwick and others, very closely allied. All right, so opportunities in healthcare. I've talked about brain imaging already. Cancer screening, I've talked about the entanglement camera, new I can't even say IVDs. Right, okay, so there's lots and lots of opportunity space to really improve healthcare. All right, so Meg, okay, it's a very early prototype of the work that the UK program did on this. Okay, you can see it's a much earlier helmet, but this particular victim is playing ping pong, and you can see how the different bits of the brain lit up as you were playing ping pong. Right, well, if you can do it with one ping pong player, that's a really dull game, isn't it? Right. And now you can see there's all sorts of opportunities in terms of understanding cognitive decision making. Okay? I love this one. This is commercialized. It came out of the University of Nottingham through our sensing hub, commercialized by Circa. It's one of the very few startup companies in quantum that's actually making a profit, by the way, at the moment, which is very encouraging. Okay. So, quantum computing, I'll not talk that much about quantum computing, but I can't resist using the word quantum apocalypse because it drives people nuts in the crypt business. All right, so if I have a quantum bit, I could have two states, 1 and 0, okay? I could put it in superposition. If I have 3 quantum bits and I put it in superposition, I've got states from 111 all the way down to 000. There are 8 of them, okay? If I have n of them, there are 2 to the n states. Yeah? So what? 2 to the n. Who cares about 2 to the n? If I had 300 bits under complete quantum control, the state space would be larger than the number of particles in the visible universe. Okay? So all we need is 300 bits under complete control. It's hard. Okay? Why does it matter? Everything we do in terms of e-trading, commercial activity, communication that's sensitive, depends on a complexity class. If you look, when you do a trade, if you buy something from Amazon, a little padlock appears in your browser, okay? And that's because what we're doing is depending on a cryptographic protocol which is assuming that something is hard, okay? And the hardness, in particular, by hardness, I mean it's not polynomial in resources. It's exponential in terms of resources. And factoring is one of them, checking you've got it right is called multiplication. That's dead easy. Okay, right. But what quantum can do through a thing called a quantum Fourier transform, discovered by a number of people, but principally Peter Shaw, showed that quantum can change that complexity class. What was thought to be hard becomes polynomially easier. Okay. So it destroys entirely our confidence in the internet were you to have a machine of that scale. Okay? So that's Peter Shaw. It means that all public key infrastructure is now dead in the water were we to have a quantum machine. Okay, no RSA, no TLS, those little padlocks, all dead. Okay? So the best estimate for a quantum computer at scale is about a decade. Okay? It's come down because of big progress with error correction and so on. How long does it take to retool all of our cryptographic primitives to be, in some sense, quantum resistant? About a decade. When do you start? Well, better start earlier. Okay? And by the way, all of the post-quantum cryptographic primitives that we're looking at have no security proof. We're putting a lot of eggs in one basket. All right, good. All right, so all I need is 300 qubits under complete control. Okay, so I've got a great chasm to bridge at the moment, and that's called error correction, error mitigation. And we're going to need probably 1 million or 6 million or 10 million of these quantum bits because we need to wrap them up into what's called logical bits where we can protect the error. That's a hell of a journey. Right, so in the UK, in my program, we are spending a lot of money. I've spent currently 1.25 billion of taxpayers' money since we started. In terms of research, we have these 5 hubs: quantum computing, quantum networking, biomedical sensing, the one I showed you already that mirrors what Warwick is doing, position, navigation, and timing, sensing, imaging, and timing. At the same time, we have 5 missions, and I managed to persuade the UK government that they would fund high-risk, high-return programs over a decade. Okay? Some of them are very ambitious. Okay? By 2035, UK-based quantum computers capable of running 1 trillion operations. It's a long shot. It might not work. Okay? But it's good to be bold. And as I've said to a number of people, I'm 78. I've looked at the actuarial tables. There's a likelihood that I will not be around to carry the can if it doesn't work by 2035. I did say that to the minister. He still let us spend the money. Okay, and in the healthcare one, which is really the complicated one, every National Health Service trust will benefit from quantum sensing. Okay, so this is our mission 3, and it is really complicated because we need to work with the Department of Health and Social Care, who are very stretched in terms of their resources. Okay, so earlier diagnosis and prevention is going to be really important for us. We know that we will be able to generate efficiencies. We'll be able to do much in terms of personalized medicine. Okay, so that's what we're up to at the moment. There are some challenges involved in this. Okay, we need to build a new community. Quantum people working with medics and with clinicians, and it's difficult. They don't have the same language, just as the QUBIC is establishing that mutuality of dialogue. That's what we're trying to do. We're sure there is a poor understanding of clinical needs, so involving clinicians is much more important for us. There's regulatory and adoption pathways to have to overcome, because if you're going to get this stuff through clinical approvals, so it moves from being a research instrument to something where you can treat patients, that's a longer journey. Right, and then you've got to manufacture this stuff and commercialize it. Right, so my final slide. I've tried to give you some examples of how, in this 100-year journey, we've actually transformed the world anyway, but there's potential for using this, if you like, second quantum revolution to do so much more. There's a huge increase in the international picture of engagement on this one. It's not just quantum computing. There's so much more to it than that. It is the UNESCO International Year of Quantum. I think we want it to be everybody's journey. Not imposed, but one where we want everybody to be engaged. It's an opportunity to learn more about quantum science, how it drives innovation, and so on. But it also influences the way we understand the world. And I think it's the most amazing adventure. We're not finished. There's lots still to do. Thank you for listening.